Srinivasan, and this is my Lab 1 report on constant velocity motion. In this experiment, I studied the motion of a tiny metal cylinder moving at constant velocity. The goal with this lab was to analyze real-world motion using video analysis and compare it to a computational model based on Newton's laws of motion. Here is my table of contents. We're going to start off with a brief introduction, then the models, then the experiment, coding, discussion, and conclusions. Some basic concepts that were part of the experiment included Newton's first and second laws, as well as the idea of constant velocity. Newton's first law says that motions stay still or keep moving at a constant speed unless a force acts on them. Newton's second law explains that when a force is applied to an object, like pushing a ball, how much it speeds up depends on how hard you push and how heavy the object is. That force is equal to mass times acceleration. If all the forces balance out, the object stays still or moves at a constant velocity, meaning that there's no change in its motion until an unbalanced force comes along. Here are some of the important equations. We have the velocity update formula, which says that the final velocity is equal to the initial velocity plus the acceleration, which can be represented as F net over m times change in time. For the position update, we have the final position to be equaling the initial position plus average velocity times change in time. For average velocity, we have that equaling the change in position over the change in time. And for Newton's second law, we have the net force equal to the change in momentum over the change in time. This is the experimental procedure. We first had to record the cylinder in motion, and then we uploaded the video into Tracker and used the software to track the cylinder's movement. We used GlowScript starter code to measure the predicted values, and we put both of the values into Excel so that we could compare them. This is the experiment setup. As a part of the experiment, we filmed the metal cylinder moving across the table alongside a wooden ruler. The wooden ruler is my reference scale, which has a known measurement to be in centimeters. The motion was one-dimensional, moving horizontally across the screen, and as a part of the project, we used the Tracker software. I was able to analyze the video to extract position and time data. Here is my position versus time graph from the Tracker analysis. From this graph, we can see that the motion shows a linear relationship between position and time, which indicates constant velocity. The slope of this line gives me a velocity of approximately 0.1 meters per second. Also on this graph, we can see the predicted line. This was created via a computational model using GlowScript and the provided starter code. This was GlowScript running on my laptop. My model is based on Newton's second law, or the momentum principle. The key assumption in my model is that the net force of the object is zero, meaning that F net is equal to zero. This leads to constant momentum and therefore constant velocity. My model parameters are as follows on the slide. You can see that the model, as you can see, the ball's mass is equal to 1, the ball's position is equal to that following vector, and the ball's velocity is also equal to the following vector, both of which we were able to extract from Tracker. We were given the time, initial time, the delta t, the rate, the net force, the ball's velocity, and the ball's updated position as well. As you can see, the model predicts a very similar linear position versus time relationship. Comparing our experimental observations with the computational model predictions, we see that there is a slight curve to the actual movement of the cylinder where there is a higher expected speed initially, but then there is a gradual loss in acceleration. This is likely due to friction on the table, slowing the movement of the cylinder over time. Our prediction doesn't take into account that loss in velocity. One of the what-if questions that was posed on the rubric was, what if I flip the coordinate axes, making positive x become negative x? In this case, it's pretty straightforward. With all the position values, while they would change sign, and so would the velocity, the actual speed or the magnitude would remain the same. In other words, the actual physics behind the scenes wouldn't really change. It would be the same linear relationship, just on a different axis. The lab report also asked us to adjust the forces involved. While again the prediction model worked well and it said the net force was 0, there could have been small forces that we didn't really account for. For example, there could have been the force of gravity, which could have had an effect if the table was slightly tilted. There could have been the effect of air resistance, which opposed the motion of the cylinder. And What we do know is that the cylinder's net forces acting on it is actually zero, regardless of whether or not I accounted for all the forces. In conclusion, I successfully demonstrated that the constant velocity of motion can be accurately modeled using Newton's laws when the net force is zero. The similarity between the experimental data and computational model reinforces both my experimental techniques and understanding of the underlying physics concepts. Thank you so much.